Today, in Project 2, we'll learn the neutral point operational mode of electric power system. And today's goal is to understand the concept of a neutral point in power system and master three commonly used neutral grounding methods and changes in voltage and current when a single-phase grounding fault occurs. Master the scope of application of three commonly used neutral grounding methods. And in today's category, we separate into 6 parts. And in the first part, we will learn the concept of neutral point in power system. And the second, we will learn the underground neutral system. And in the third, we will learn the neutral point is grounded by the arc suppression coil. And in the fourth, we will learn the neutral direct grounding system. And the fifth is the neutral through independence grounding system. And of course, in the sixth, we'll have a little summary of this period. Okay, in the first period, we'll learn the concept of neutral point in power system. Concept of neutral point in power system, you can see this is the two basic picture of electric power system. And it's the neutral point of transformers and generators whose three-phase winding are star connected. Neutral grounding methods of power system is the electrical connection method between the neutral point of the power system and the earth, also known as the neutral point operation mode. The neutral point grounding method of the power system is related to the voltage level, single-phase grounding short circuit current. Over voltage level, relay protection and automatic device configuration, which directly affect the installation level of the power grid, the reliability and continuity of the system power supply and the main transformer and generator operation, safety and interference to the communication system. Neutral point operation mode of power system. We have neutral point operation mode of power system. Neutral is not effectively grounded, which is also called small ground system. And the neutral point is effectively grounded, is large ground system. And we separate into different two parts. And in each part, we divide it into 3, and which are ungrounded neutral system, and the neutral point is grounded by the arc suppression coil, and neutral via high resistant grounding system, neutral direct grounding system, and neutral via low resistant grounding system, neutral point through small impedance grounding system. According to the magnitude of the grounding capacitance current when a single-phase grounding fault occurs, the neutral point operation modes of the power system are divided into 2 categories: neutral point non-effective grounding and the neutral point effective grounding. The neutral point is not grounded. The neutral point is grounded through the arc suppression coil, and the neutral point is directly grounded. And in the second, the ungrounded neutral system, well, the content, we have 4 parts. The first part is normal operation, and the second is in case of single-phase earth fault, and the third one is features of scope of application, and also we have a little summary about that. And which is the normal situation is when the power system is in the normal operation. It's generally considered that the 3-phase system is symmetrically, which is the 3-phase voltage is symmetrical. The voltage is the same size, the frequency is the same, and the phase difference is 120 degrees. The neutral point voltage UN is 0, which is the formulations about here. ICU equals to ICV and also equal to ICW, and omega CU times U is equal. The distributed capacitance of each phase conductor to ground is equal and equal to C, and the effective value of each phase to ground capacitive current is also equal and symmetrically under normal condition. And the total capacitor current is 0. And you can see the photographs over here. The graphs show how the mass calculate, how you do the math. And the single phase ground fault, which is also called the W phase metallical grounding. The faulty phase is 0. And also the neutral to ground voltage is equal in magnitude to the ground phase voltage, but in opposite direction, rising to line voltage. The voltage change, the non-faulted phase voltage becomes the line voltage times the phase voltage. The phase-to-phase voltage, which is the line voltage, remains unchanged and the electrical equipment is not affected and can continue to operate for 1 to 2 hours. The green bar is the line voltage during normal operation and the right box is the line voltage after fault. You can see it over here. And we have also showed some picture of the normal routine vector graph and also the vector diagram for single phase to ground fault. Each phase capacitance current change, the fault phase current is 0. The non-fault phase current rises to the original times 3. The phase leads the corresponding voltage by 90 degrees. Note, and we have a little special hint over here. The green is normal phase current, red is single phase current after fault. And each phase capacitance current change, the ground point capacitance current is 3 times the ground capacitance current in normal operation. And the note is the blue is the sum of the ground point capacitance current. Also, in each capacitance current change, we have a formula to calculate. It is the particular calculation formula of single phase grounding capacitance current. You can see up here. And also, we have a vector picture of for single phase to ground fault. And what is special and how it uses it is, you can see the high reliability of power supply can bring people can continue to run for 1 to 2 hours after a fault occurs, and reliability of power supply is high. However, the signal is issued by the AC installation monitoring device to notify the operator. Increased investment after the fault, the non-fault reality to ground voltage increase the line voltage, and the equipment and the line to ground installation are considered to be able to withstand the line voltage and investment increase on grounded neutral system. And the features and the scope of application. On the grounded neutral system, reinforced concrete or metal steel tower with no direct connection to generator, or system no direct connected generator, non-reinforced concrete or non-metallic steel towers, and non-refined concrete or non-metallic steel towers, and the cable line. You can see, and the line is not long, the voltage level is not high, the grounding capacitor current is small, and the arc can be extinguished by itself, and the system below 35 kilovoltage can use the neutral point ungrounded system. And we have a little summary about ungrounded neutral system. You can see in the event of a single phase grounding fault, since the line voltage remain unchanged, there is no impact on the power user, and the user can continue to operate, improving the reliability of the power supply in order to prevent the expansion of the fault range due to the arc at the grounding point and accompany over voltage. An AC installation monitoring device must be installed in the system when a single-phase grounding fault occurs. A single of installation job is immediately sent to notify the operation on duty. Staff deal with it in a timely manner. The relevant regulation of the power system stipulates that when a single-phase grounding occurs in a three-phase system where the neutral point is not grounded, the allowed continuous operation time should not exceed 2 hours, and monitoring shall be strengthened. Okay, and in the third section, we will learn the neutral point is grounded by the arc suspension coil. And in this concept, we will learn the normal operation and the working principle of arc suspension coil, and in the case of single-phase earth fault, and the feature and the scope of application. And the normal operation, the arc suspension coil is installed between the neutral point of generator or transformer in the system and the earth. During normal operation, the three-phase system is symmetrical and the neutral point to ground voltage is zero and the current flows through the arc suspension coil. When single-phase grounding, the total current at the grounding point is the sum of capacitor current and inductor coil current. The capacitor current leads the voltage by 90 degrees and the inductor current lags the voltage by 90 degrees, and the two currents cancel each other in opposite directions. Selecting the proper tap can reduce or zero the current at the grounding point. And there's the arc suspension coil compensation method. How to do it? We can use full compensation is to make the inductor current equal to the ground capacitor current and the zero current at the ground. However, under certain condition during the normal operation, a series resonance may form, resulting in a resonance over voltage and compromising the insulation of the system. And the arc suspension coil compensation method, which is have this equation have to work, and you can continue the next step. And how the voltage change, the faulty phase voltage is zero. The neutral to the ground voltage is equal in magnitude to the ground phase voltage, but in opposite direction. Non-faulty phase voltage becomes line voltage. The phase-to-phase voltage remains unchanged. Electrical increment is not a fact and can continue to operate for 1 to 2 hours. And the features of this is that we have two important features. One is high reliability of power supply, and the second is the fault current at a single phase grounding is reduced. The arc can be quickly extinguished, and damage to the equipment caused by the arc over voltage is prevented. And the third one is increased investment. Okay, so the summary of the neutral point is grounded by the arc suspension coil. You can see when a single-phase grounding fault occurs in the neutral point through the arc suspension coil grounding system, the operation is allowed not to exceed 2 hours. If the grounding point cannot go through the arc suspension coil grounding system, the operation is allowed not to exceed 2 hours. If the grounding point cannot be eliminated within this period, the grounding part of the line should be powered off. The smaller the power outage range, the better it is. And the fourth, we'll learn the neutral direct grounding system, and we also have to learn normal operation and in case of single-phase earth fault and the features and the scope of application. So the normal operation is during the normal operation, the three-phase system is symmetrical. And when the neutral point is directly grounded, the ground resistance is approximately to zero. So the potential between the neutral point and the ground is the same. And we also have two voltage and current changes we showed above. And when if you want to learn more about it, you can read by yourself. Okay, we'll send this PowerPoint after the class. And mostly we have the features of this, and we have advantage and disadvantage. So the advantage of this is low invest cost, and after the fault, the non-faulty phase to ground voltage is kept as the phase voltage. But you also have the shortcoming, which is the disadvantage. The single-phase short circuit current is very large, and power supply needs to be interrupted as soon as possible, and the reliability of the power supply is very low. And the scope of it is widely used is system of 110 kilovoltage and above. And the fifth, we will learn the neutral through impedance grounding systems. We also have to learn these three parts. And the feature of this is that the resistor is an energy consuming element, which is discharge channel for the capacitive current of the system to the ground. The system resonance over voltage caused by various reasons can be eliminated. The installation requirements are low, which can be reduced the construction cost of the power grid by 10% to 20%. And the scope of this are 35 kilovoltage and 10 kilovoltage. Urban power grids with cables as the main body. The size of the grounding resistance is appropriate to limit the grounding phase current within the range of 600 to 1000. And now we have a class summary. So in the neutral mode of operation, we have neutral non-effective grounding system, which we call small current grounding system. And also we have neutral point effective grounding system, which also called high current grounding system. And we separate it into three parts, and we have the scope and the features of them, and we show the chart about this, and you can learn after school. And this is mainly about this class. And we have a little exercise for you. You can do the math after the school. And we have also the solution of it. Okay. If you're interested, you can do it after the class. And thanks for learning. And Mr. Chen, we'll see you next class.